Have you ever stopped to think about why your hot coffee always inevitably gets cold? Or why a car, any car, needs an exhaust pipe to run? It turns out the answers to those questions, and so many others, are governed by this set of universal rules. And these aren't laws made by people, they're the laws of thermodynamics. They control, well, everything. So let's pull back the curtain on the unbreakable rules that run our entire universe.
For centuries, people have been obsessed with this idea of the ultimate machine, one that could just run forever with zero fuel. A perpetual motion machine. But no one has ever succeeded. So why not? What is this fundamental law of the universe that they keep slamming into? Well, to solve this little mystery, we need to understand the rules of energy.
Before we can even begin to crack that code, we need to learn the language it's written in. And for us, that means getting a handle on a few key ideas from the world of thermodynamics.
So, first up is this idea of a system. Now, in physics, that's just a fancy way of saying the specific blob of stuff we're looking at. It could be the gas trapped inside a piston, the water boiling in a kettle, or hey, even an entire star. We just draw a line around it and look at its properties.
And how do we describe the condition of that system? We use what are called state variables. The best way to think about these is like the system's vital signs: its pressure, its volume, and its temperature. They tell us everything we need to know about what's going on inside.
Right, so this here breaks down how these systems can interact with the outside world. An open system, like your morning cup of coffee, is letting out heat and steam, right? So it's exchanging both energy and matter. A closed system, like a sealed water bottle, can get warm or cold, but the water's not going anywhere. It exchanges energy, but not matter. And then you have the Holy Grail, an isolated system. Think of a perfect thermos. It exchanges absolutely nothing. This distinction, it's going to be super important in a minute.
All right. Now that we've got the basic vocabulary down, we can tackle the first unbreakable rule. This is the first law of thermodynamics, but honestly, you can just think of it as the universe's strict, no free lunch policy.
So the law basically says that energy can't be created out of thin air, and it can't just disappear. It has to be accounted for. If you put heat energy into a system, it has to go somewhere. You can't get more energy out than you put in. The universe is like a very strict accountant.
And this is a brilliant way to picture that accounting. Think about your own personal budget. The heat you add, that's DQ, that's your income. That money, that energy can only go to two places. Some of it increases a system's internal energy, DU. That's like putting money into your savings. The rest is used to do work, DW, like pushing a piston up. That's your spending. It's that simple. Income always equals savings plus spending.
So the big takeaway here is this. The first law completely kills the idea of a machine that creates its own energy. You can't get something from nothing. The absolute best you can do is break even. And, as we're about to find out, you can't even really do that. This is the law of conservation of energy, plain and simple.
Okay, so we know energy is conserved. You get what you get. The next logical question is, how can we actually manipulate a system to make that energy do something useful for us? Well, it turns out there are 4 main strategies, or processes, and each one has its own little rulebook.
And this table lays them out beautifully. If you run an isothermal process, you keep the temperature perfectly constant. That means any heat you add has to be immediately turned into work. In an adiabatic process, you insulate the system completely. No heat in or out. So if the system does work, it has to pay for it by using up its own internal energy, and that makes it cool down. Isochoric means constant volume, so the system can't expand or contract. No work is done, and all the heat you add just goes into raising the temperature. And finally, isobaric keeps the pressure constant, which means the heat you add gets split between doing some work and raising the internal energy.
Okay, we have all the clues. We know what a system is, we know the no free lunch rule, and now we know the different playbooks for using energy. We can finally put all the pieces together and solve the mystery of the perpetual motion machine.
And this right here is what it's all been building towards, the heat engine. We're talking about everything from the original steam engines that powered the Industrial Revolution to the engine inside your car right now. They all operate on this one fundamental principle: turning heat into useful motion.
And every single heat engine in existence has these 3 non-negotiable parts. You need a hot source to provide the energy, fire, a nuclear reactor, whatever. You need a working substance, usually a gas, that can expand and actually do the work. And, this is the absolute crucial part, you need a cold sink to dump all the leftover waste heat in.
Hey, look familiar? It's our budget again. The total heat you take from the source, Q1, gets split. Part of it becomes useful work, W, but some of it, Q2, must be thrown away into the sink as waste heat. It's unavoidable. There's always going to be a leftover energy.
So to figure out what the absolute best-case scenario could ever be, a brilliant physicist named Sadi Carnot came up with this idea of a perfect, completely idealized engine. The Carnot engine isn't a real machine you can build. It's a thought experiment. It's the theoretical benchmark that shows us the maximum possible efficiency any engine could ever hope to have.
So, this perfect engine runs on a perfect four-step cycle using the processes we just learned about. It smoothly expands at a high temperature, soaking up heat. Then it expands some more while it's isolated, cooling down. Then it gets compressed at a low temperature, dumping waste heat. And finally, it gets compressed the rest of the way back to the start, heating up again. It's a completely perfect, reversible loop.
And this is the absolutely mind-blowing conclusion that Carnot reached. The maximum possible efficiency of any heat engine you could ever dream up doesn't depend on the gas you use or how clever your mechanical design is. It is fundamentally limited by one thing and one thing only: the temperature difference between your hot source and your cold sink. That's it.
This simple, incredibly elegant formula says it all. The efficiency, that's eta, is equal to 1 minus the temperature of the cold sink, T2, divided by the temperature of the hot source, T1. So, if you want to get the highest efficiency, you need that fraction to be as small as possible. You need the biggest possible gap between hot and cold.
And this right here is the final nail in the coffin. For that efficiency to hit 100%, that fraction, T2 over T1, would have to be 0. And for that to happen, the temperature of your cold sink, T2, would have to be absolute 0. But reaching absolute 0 is physically impossible. You can get close, but you can never get there. And because of that, no heat engine can ever be 100% efficient.
So there it is. A perpetual motion machine is impossible. First, because you can't get something for nothing. That's the first law. And second, because you can't even break even. You always have to pay an energy tax to the universe in the form of waste heat. And that leaves us with one last big thought. If every single energy conversion, in every car, every power plant, everywhere, inevitably creates this waste heat, what does that inescapable inefficiency mean for the future of our planet?